Hi everyone, welcome back to my number sense series. In this video, we're going to talk about converting from decimals to fractions. Now, there's a lot of things that are involved with converting decimals to fractions. So today we're going to learn basically the basics of these. We're going to learn things like 1 over 2, 1 over 4, 1 over 5, 1 over 8. 1 over 3 is somewhere over here. 1 over 6, 1 over 9, 1 over 11. And basically every number from 1 to 10, except for something, 1 over 7. You might notice that 1 over 7 is never mentioned here, and that is because it's going to get its own video, because 1 over 7 is such a special fraction that has really cool properties that I think it deserves its own video. And also it can be confusing at first. So yeah. Today we're just going to focus on 2, 3, 4, 5, 6, 8, 9, and 11. So let's get started with 1 over 2, the easiest one. How do we convert 1 over 2 to a decimal? Well, hopefully, if you know the basics of decimal to fraction conversion, you'll have this memorized, but in case you don't, here's how it actually works. In order to convert something from a fraction to a decimal, the actual process involves turning the denominator into a power of 10. For example, 1 over 2, what we do is we multiply the top and the bottom of the fraction by 5. This makes it equal to 5 over 10, and we know how to convert something over 10, right? It's just 5, but with this decimal place moved over once. So 0.5. Now it's something similar with 1 over 4, right? But this time we can't convert the bottom into a 10, we have to convert it into a 100. Because 10 is not a multiple of 4, but 100 is. So we multiply the top and bottom by 25, and what we get is 25 over 100. And this is going to be 25. And the decimal point is over here, but since it's over 100, we move it over 2 times, so it's 0.25. Now, given that 1 over 4 is 0.25, you might be wondering, okay, well, what's 2 over 4 and 3 over 4? Well, 2 over 4 is just 1/2, so what's 3 over 4? Let's see if you can figure it out by yourself. What is 3 over 4? Well, to get from 1 over 4 to 3 over 4, we should be able to realize that we just multiply by 3. So let's just multiply 0.25 by 3. And what do we get? Well, 25 times 3 is 75. So it seems reasonable that this is 0.75. And that is correct. Now, there's something very similar that goes on for 1 over 5, but even easier than 1 over 4, because this time we can still convert the denominator into a 10. So if we multiply the numerator and the denominator by 2 this time, what we get is 2 over 10, or 0.2. Now given that 1 over 5 is 0.2, what is 4 over 5? Well, once again, using similar logic, we should just multiply 0.2 by 4 to get to 4 over 5. 0.2 times 4 is what? Well, 2 times 4 is 8, so 0.2 times 4 is 0.8. Now, 1 over 8, this is going to be the hardest one in this half, but once again, we just have to turn it into a power of 10. But notice with 2, we have to go to 10, with 4, we have to go to 100, with 8, we have to go to 1,000. And if you don't have this memorized, this is a very good time to memorize this. 1,000 is 8 times 125. So if we multiply the top and bottom by 125, we get that the decimal form of 1 over 8 is 0.125. Also notice that we could have just gotten it by dividing 1 over 4 by 2, but this is, I hope, more informative. Now, given that 1 over 8 is 0.125, what is 5 over 8? Well, once again, we're just doing some multiplication here. What is 0.125 times 5? Well, 125 times 5 is 625, so 5 over 8 should be 0.625. So that is it for this half of the board. And now it's time to talk about why there are 2 halves of the board. 1 over 2, 1 over 4, 1 over 5, 1 over 8. Those are all on this side of the board. And why? Well, it's because these are kind of, in a sense, the nice decimals. These are the decimals that are finite, the ones that have a finite number of digits. All of the fractions over here are what we call like non-terminating, infinite decimals, because they have an infinite number of digits that you can never write down. These have a finite number of digits. Why? Well, it's because in order for something to have a finite number of digits, you have to be able to represent it as just something over 10 to the power of something, right? That should be hopefully like obvious. Like 25 over 100 is 0.25. But if we had like an infinite number, well, it doesn't make sense to have an infinite number in a fraction. So an infinite decimal should not be able to be represented as like something over 100, if that kind of makes sense, right? So why can't we represent these as something over 10 or 100 or 1,000? Well, it's because the numbers here aren't, quote, made up of 2's and 5's. For example, notice 9, right? 9 is 3 times 3. If we wanted to make it into a 10 or a 100 or a 1,000, what can we possibly multiply 9 by in order to make 10, 100, or 1,000, right? 9 is a multiple of 3. So any multiple of 9 is also going to be a multiple of 3. But 10, 100, and 1,000, those are never multiples of 3, only multiples of 2 and 5. So we can never convert this into something over a power of 10. And similarly to this and also this, the only fractions that are terminating, that are finite in decimal form, are the ones where the denominators are made up of only 2's and 5's, the products of 2's and 5's. For example, 2 times 2, 5, 2 times 2 times 2. For example, something over 10 would be something over 2 times 5. So those are going to be terminating. Those are finite because you can represent them as fractions. Hopefully that kind of makes sense. Now, how do we do these? If they are infinite, how can we possibly determine what they are or write them down? Well, the nice thing with these is that they follow a very fixed pattern. But what is the pattern? Well, let's find out. 1 over 9, how can we figure out what 1 over 9 is? Well, recall that fractions are really just division, right? So 1 over 9 should be equal to 1 divided by 9. Well, what's 1 divided by 9? Let's do some long division. If we divide this by 9, what do we get? Okay, well, let's see. This is 10, so 1, drop the 9 down, 10, oh, another 1, 0.9, oh, 1, 0, whoa. And, it should be kind of obvious that it is 0.111111111 going to infinity. And we will write this as 0.1 bar. Or 0.11 bar, whichever you prefer. They mean the same thing because the bar means that digit is repeating. So that's 1 over 9. Well then, if that's 1 over 9, then what's 2 over 9? Well, it's similar logic to these problems over here. Don't be intimidated by the fact that this is an infinite decimal. It still operates by mostly the same logic. So to get from 1 over 9 to 2 over 9, we multiply by 2. So we should multiply 0.111111 repeating by 2. Well, if we multiply 1 by 2, we just get 2. So it should be 0.222222 repeating. Or 0.22 with a bar over it. Or 0.2 with a bar over it, whichever you prefer. So we are going to do a similar process for 1 over 6. Please try this on your own if you can. Or you can watch my explanation right now. 1 over 6. Let's see. Let's attempt the long division. If we divide it by 6, we have 0 point, and then 10. So that goes into it once. And we get a 40, right? 40, 6 goes into 46 times. 40. And now we see that this repeats, right? And it's still a 6, so this is going to repeat again. It's 0.166666 repeating. Or here we would write 0.16. Notice the important part, that there is only a bar over the 6 because the 1 does not repeat. The 1 is just there at the start, and then the 6 is repeat until infinity. So we only put a bar over the 6 because that's the repeating part. Now, here's a bit of a more difficult question. If this is 1 over 6, then what is 5 over 6? Notice that this time, the multiplication has some carrying associated with it, and carrying with infinite decimals is kind of difficult. But there are ways to get around this. First of all, you could just divide 5 by 6 using long division, and then you would get the answer. Or what you can do is think of 5 over 6 as 1 minus 1 over 6. If you do that and set up the subtraction, what you'll get is 0.833, where the 3's will repeat. Very nice. Now, for the final one, 1 over 11. 1 over 11, To derive 1 over 11, we once again just use this idea of repeating. So 1 over 11, what do we get? 1.000 divided by 11. Well, it's going to be 0.0 because we have to go to this 100 thing now. That goes into it 9 times. So 99, 10, 11 doesn't go into 10, so we put another 0. And now we see that this 100 thing once again repeats. But it doesn't repeat like 0.099999 because there's a 0 in between. So what it actually repeats like is 0.090909 to infinity. This is how it goes. And so 1 over 11 is equal to 0.09, where both digits are repeating. And this pattern is something that we are going to cover more in a future video about repeating decimals. But this is interesting. And now, what is 7 over 11 equal to then? Well, if you want to multiply 0.09090909 by 7, the way I've said it should kind of give you a hint as to how you should do it. Because 09 times 7, what's that? That's 63. 63, 63. Notice that there's actually no carrying involved because this 0 acts as a little bit of a buffer. So it's going to be 0.63636363. And once again, we are going to learn how to derive this very easily and a lot of other relations in a future video about repeating decimals. For now, this is the basics. And now one final thing. You might remember that I said we were going to talk about 1 over 3. Well, there's no 3 on the board right now, so where's 1 over 3? Well, it's actually right here, 1 over 9, because 1 over 3 is just 3 over 9, right? So we should be able to derive 1 over 3 from here. And indeed we can, because 1 over 9, well, to get to 1 over 3, we just have to multiply it by 3. So that reasons to follow that 0.333 repeating must equal 1 over 3. Now, one final tidbit that some people get stuck on and an interesting idea about math is what happens if you multiply this by 9 on both sides? If you multiply by 9 on both sides, what do you get? You get 9 over 9 equals 0.9999. So 1 equals 0.9 repeating? How is that possible? Well, there are a few ways to explain this. But the most mathematically correct way, I think, is to say that 0.999 repeating is not a very well-defined number. But here's an idea. If you think that 0.999999 repeating to infinity and 1 are different numbers, then try to find a number that's in between them. Spoiler, you can't. So in math, we would say that they are equal because you can't find a number that's between them. And also the real numbers are dense. So that is the basics of converting fractions to decimals. In this video, we covered 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 8, 1 over 9, and 1 over 11. And hopefully you know 1 over 10 by yourself. So that is going to be it for today. Thank you guys for watching, and I'll see you next time.